One of the most difficult concepts to try and understand or differentiate between in physics, in my opinion, is potential versus potential energy. They sound very similar. However, there's a fairly important distinction between those two terms. Part of the reason why potential is so hard to understand is we've dealt with potential energy when it comes to gravity and gravitational fields. We didn't really talk about what's called gravitational potential because it doesn't really have much use to us in terms of the analysis that we wanted to perform. But there is something called gravitational potential. It is different than gravitational potential energy, even though they sound very similar. So I want to quickly explain to you what gravitational potential is so that when we apply it to an electric field, we can better understand what electric potential is. And that is something that is used much more frequently than what we call gravitational potential. But let me start with that because I think most people have a more innate understanding of gravity as opposed to electricity and electric fields. So let's take a look here to try and understand this distinction by noting that we have three masses, A, B, and C, which are 5, 10, and 20 kilograms respectively. All three are being held 2 meters above the floor of this classroom, which we will assume is on Earth. We know that the potential energy is found by multiplying the mass times the acceleration due to gravity and multiplying that by the height. So if we plug in those values, we get 98.1 joules for mass A. If we do the same with B using the 10 kilogram mass, we get 196.2 joules, and we get 392.4 joules if we do that for mass C. So that makes sense. More mass yields more potential energy. If, however, we want to look at what I kind of call like the unit price, so if you buy a crate of eggs, you can take the total price, but you can divide it by the number of eggs and determine how much it cost you per egg. We can do the same thing, but let's find out how much energy we got per kilogram of mass that these objects had. So if I divide the 98.1 by 5 for 5 kilograms, I find that object A really has 19.62 joules per kilogram that it possessed. If I do the same for the second, this time dividing by 10 because it's a 10 kilogram mass, I will find that I get that same value, 19.62 joules for every kilogram that that object had. And if I do the same with the last mass, instead dividing by its mass of 20, you'll find that once again, I get 19.62 joules per kilogram. So what we're finding is anywhere along this line that an object is placed, it seems to be getting 19.62 joules per kilogram that it possesses. And that's exactly what we call the potential. One of the reasons I guess they call it potential is it's the potential to have potential energy. It's the rate by which you will get potential energy if you show up. So that if is kind of like it's potential, it may happen. So it's kind of like the potential to have potential energy. So it's kind of weird how they're both very similar sounding terms, but the potential is like the rate at which you'll gain energy based on how much mass you have. We can eliminate the masses then and just recognize that anywhere along that line is going to have what we call a gravitational potential of 19.62 joules per kilogram. So what that really is telling us, again, is the rate at which energy will be gained by a mass when that object is placed in the field. So the potential is always there in the field. The mass gets the energy, the potential energy, when it shows up at that location. But the potential is a property of the field itself, and the energy is a property of the mass or the charge, depending on what we're looking at. So just to give you a more technical definition here, the potential is the rate at which energy will be gained when an object, a mass, a charge, etc., is placed in the field. It's very important to understand that is a property of the field. You can remove all the objects, all the charges, all the masses, the potential is still there. Because when you place those objects back, they then will have energy based on those locations. So that potential is always there. The potential energy itself is the physical energy that's possessed by the mass, the charge, whatever we're talking about, once it's placed in the field. So that is a property of the object itself. It seems like a small distinction, very important to understand. One of them is a property of the field, the other is the property of the object, be it the mass, the charge, whatever we're placing in this field. I think one of the easiest ways to understand that is with an analogy. So this is my ShopRite analogy. Let's assume that you worked at ShopRite and you were a cashier and you were making $10 per hour. Well, if you're making $10 per hour and you work 1 hour, you will physically take home $10 in your pocket. If you work 3 hours or 10 hours, You bring home $30 or $100 respectively. That would physically be money that you now possess. ShopRite wouldn't possess that. You would physically possess that. You'd walk away with it. ShopRite would be the one who's determining the hourly rate. Now, in this analogy, the actual money that you, the worker, takes home that you now physically possess is like the potential energy. You got that because you showed up at a location at which you could earn money, and then based on how long you worked, you took that money with you. The potential analogy here would be the hourly rate. It doesn't matter if you work 1, 3, 10, or 100 hours. Your hourly rate will always be the same. For every hour you work, you'll make the same amount of money at that location. So the $10 per hour is a property of ShopRite. ShopRite determines that. And the dollar amount that you physically take home, that's a property that you now possess. That is money that you can now possess and put towards whatever you want to do with that money. If you do want to experience a new potential, you want a new hourly rate in this analogy, you had better find a different location within the company. So if you now work as a manager, you make $50 per hour, you are now higher up in the company. In this case, both physically, because you're higher up, but you're also higher up in terms of the potential. So now as a manager, you could work the same 1, 3, and 10 hours, but you're going to possess physically different amounts of money than you did when you worked at a lower position. Once again, the physical money being possessed is the potential energy analogy here, and the hourly rate is the potential. The more hours you work, the more money you have. Just like the more mass or charge you have, the more energy you will acquire. However, the rate at which you gain that energy is independent of the mass or the charge that you bring, because it is the rate based on those quantities. So when it comes to potential energy, what we want to realize is if you have a mass and you hold it higher up near the ceiling, it'll have more potential energy because H from the ground is much higher. And if you hold that mass lower, it has less potential energy. So what we can do is, even if you remove those masses, we can point to the ceiling and say that is a high potential region, meaning that area has the potential to give a mass a lot of potential energy if I placed it there. That is a region where the most energy will be given to a mass. Whereas near the floor, we say is a low potential region. If I hold a mass down there, it will get some energy, but not as much as it would near the ceiling. So we simply call that a low potential region. If you take a look here, the masses themselves have the energy. The field has the potential, or the potential regions. One of the questions that I highly recommend you get in the habit of asking yourself, and this is for when you want to determine, when you're moving through a field, am I gaining energy, losing energy? Am I increasing a potential, decreasing a potential? A simple question you'd like to ask yourself is the mass or the charge doing what it naturally wants to do? Now, I know they don't want to do anything. They're not sentient. But we want to imagine if I let go of a mass, it's going to drop downwards. So that's the natural motion it wants to take. So if we take a look here, if I lower a mass towards the ground, if the answer to that question is yes, I'm allowing this mass to do what it naturally would like to do, then we know that you are going to be losing energy. Just like a mass loses energy as it falls towards the ground, if I move a mass under my own power towards the ground, I'm moving in the direction it naturally wants to go, and its energy is decreasing. Alternatively, if I were to raise that mass near the ceiling, that is not a natural motion. That's opposite the direction it naturally wants to move in. And because I'm increasing the height from where it would like to be, I'm therefore increasing its energy. And the same goes for potential as well. If I'm moving upwards towards the ceiling in space, I can say I'm moving towards a higher potential region because that is not a location. I'm moving to a location that a mass would not naturally want to be in. If I go from the ceiling to the floor, we say there's a decrease in potential because now I'm going from a region that a mass would not want to be in naturally to an area where it naturally would want